Hey guys, so I'm going to go ahead and talk to y'all a little bit more about the atomic emission spectra and electrons. So we may or may not have done the lab yet, but I want to go ahead and talk to y'all about the atomic emission spectra. So atomic emission spectra, well, we haven't really learned about radioactivity because it's not one of our standards in chemistry, but if you had a nucleus that was unstable, because it has too many protons and neutrons in there, we did talk about how crowded the nucleus is, then something's going to have to give. That nucleus is going to release some particles in the form of radiation. It's very similar to that. If you have an atom, and now it's the electrons that are absorbing energy. If the electrons absorb too much energy, well then they're going to have to release that extra energy in some form, and it actually releases the energy in the form of light. Okay, so if it's not stable, it's going to have to release that energy. It's kind of like if a student is drinking an energy drink. They want energy, so they take in all that caffeine, right? Well then, that student is not stable. They have taken in so much energy, it's usually going to drive somebody crazy, and they got to release it. Usually they're releasing it by talking or they're moving around. So very similarly, if an atom absorbs too much energy, then it has to release it, and the form it releases it in is usually light. Okay? If we take that light and we pass it through a prism, then it breaks it up into the individual bands, and I've got a slide I'm going to show you in just a minute about that. That is called the atomic emission spectrum. So an atomic emission spectrum, just like we talked about in the last lesson, it's unique. It's like a fingerprint for every element. So each one has its own specific bands of light that are emitted. So emitted is just something that's given off. This is also the way that we identify stars and planets. You look through one of these little prisms. It's a different, I forget the name of the device, but it's like a prism. You look at the star and you can see the different bands of light that are being emitted, and you can tell what elements are in the star itself. So only specific colors of light are emitted. That's related to its frequency. We talked about this in the last lesson where the speed of light, okay, is this going to let me write? No, because it just wants to be wonky like that. So the speed of light, which is c, is equal to the wavelength of light times the frequency. Well, we have this equation. I told you guys that we weren't going to have to actually do this math, but the energy of light is equal to a constant times the frequency. And if you do some substitutions here, you can take the frequency or the wavelength and make it related to the amount of energy. Okay? So that's how the color of light is related to the frequency. So here's an atomic emission spectra. In this emission spectra, let me see if I can grab this and move it. No, of course not. So it looks like this. You have some unknown chemical here, and then you have different known substances with their own bands of light. And if we were to take this unknown right here, this one on top, and we were to find something with those same exact bands and tried to match it up with either beryllium. Does it look like beryllium? No. There's copper, there's manganese, strontium, and titanium. You'll see that the unknown is actually going to be strontium because those bands of light are the same. So see, this looks a lot like a very unique fingerprint of bands of light for each element. Okay? I went too far. I did. So here's an explanation of why we get different bands of light. So these bands of light have to do with different electrons. Electrons are on different energy levels. Those are the rings around the nucleus. And depending on whether or not something jumps from a lower energy state to a higher energy state, so many bands away, so if it goes from like the first ring to the third ring, then it's absorbed 2 quanta possibly of energy, and then it's going to go down just to 1 band, okay? And that's going to be a specific amount of light. So there are predictions, there are calculations that can be made. We talk about this sometimes in AP chemistry, but whatever amount of light that electron jumps from one band to another, it's going to release a certain wavelength or frequency of light, and then you get these different colors. All of those collectively are what the atomic emission spectrum is. Okay, so it's typically different electrons that are being released with different energies associated with them. Okay? All right, so this is just a larger diagram of something that we were just looking at. However, what I thought was really interesting is we can now take these different energy levels and we can make it kind of look like, I know it sort of looks like a half circle, but we can take this and we can make a smaller diagram looking at just energy level 1 through actually 7, which is the highest energy level that our orbitals or rings can go to. Okay? And then those electrons would jump from like energy level 1 to 2 and then back down. Or in this case, it goes from energy level 3 to 2, which makes a red color. Or if it jumps 2 energy levels from like 4 to 2, then you've got a bluish green wavelength or frequency of light. And these collectively, like I'd already said, make our atomic emission spectra. So something that I thought was really cool, let me just really quickly move this over because I tried to make these things a little bit smaller, and when I did that I moved the slides over and apparently I made it get a little wonky. So for this we have 2 electrons that are I'm sorry, let's go back. So just explaining how these happen. Step 1, an atomic emission spectrum occurs by first you have electrons that are absorbing too much energy. Like I'd already said, if they absorb too much energy, it's kind of like you. You're not going to be stable. You're going to want to get that energy out. So what happens? The energy has to come out. So step 1, you take the energy in. Step 2, they've now become unstable. They have to release the energy. Okay? That amount of energy, or the particle that's absorbing the energy, is now a photon. Okay? And those photons are going to be released, and the photon is that energy, electrons that absorb the extra energy. That energy is stored as a photon, and just like photography, the photon of light is what's being released. So it has a specific amount of energy associated with it. Those specific amounts are called quanta, and the photons, step 3, are being released. So to recap that, we have an electron, okay, down here. This is called ground state. There's another diagram you can copy in just a minute. So here's an electron down here. It's at the ground state. Ground state is going to be the most stable state. So electron is at ground state. Well, you give the atom energy. It can be in the form of fire or heat or something like that. And so you are going to make it go up to a higher energy level. Well, now it's in an excited state. It's not stable, has all that energy, okay? And then it has to become stable. It's got to go back down to ground state because nature favors stability. To go back to ground state, it's now going to release energy. How? It releases the energy as photons of light. Okay, those photons are those little packets of light that also carry with them a quantum of energy. A quantum is just a specific amount. And it's releasing that. However much energy is released is related to the color of light that's absorbed. Okay? So this was the slide that I showed you guys. I think it was in yesterday's lesson. So in our previous lesson. So again, the atomic emission spectrum, you should probably copy all of this because it's really useful. It gives, in a nutshell, instead of a really difficult, complex diagram, you have something like this. And I call this the ladder diagram. I'm going to pull this back up. But I call this the ladder diagram. In this ladder diagram, it's explaining how electrons give off light in an atomic emission spectrum. This is actually one of our standards. Okay? So first, we basically draw this blue ladder. Okay? So this ladder is that little window of the different energy levels or orbitals in an electron cloud. Within these different levels, it can go up to 7, but you get the gist of it with like 4 of these. So I just do N equals 1. N is the energy level, and 1 is the ground state. That's stable. And then you have 2, 3, and 4. Okay? So step 1, your electron absorbs too much energy. It absorbs energy, it becomes unstable. Step 2, it's got to release that energy as a photon of light. So when it's absorbing energy, we draw a dot with an arrow pointing up. Okay? Then, this was just my stopping point. I probably should have put my dot there, but then you've got a squiggly line to show that that's a different way of energy being represented. This is basically like heat energy, and then this line right here that's squiggly, well, that's light energy. And that's how scientists give an indication that this is the light form of energy with just a squiggly line. Okay? So the squiggly line with an arrowhead pointing down, that's just showing that it's releasing a photon of light. What you guys need to understand for a test is you can either use this diagram or you can give a written explanation of this. A lot of people prefer the visual diagram because it just makes sense. It's kind of like if I'm climbing a ladder, on the bottom of the ladder is more stable. That's on the ground. If I climb higher up on a ladder, well then it's less stable. And if I fall with more energy the higher up I go. Okay? So that's why that's kind of a useful analogy. Alright, so if you don't have enough time to copy this, if you haven't been writing while I've been talking, then go ahead and pause this and copy this down, okay? Time to move on. So, let me move this over again because that is just not, I don't like it looking like that. Okay, so as far as photons go, photons are just basically the way that electrons behave when they're behaving as particles. Okay, so electrons can behave like particles and waves, and the electrons are giving off this energy as light, and the light particles are called the photons. Okay, so a quantum is basically your amount of energy that is being gained or lost by the electrons. Okay, and then you have photons, which is a particle of EM is electromagnetic radiation. They don't have a mass, okay, but they do have a quantum of energy associated with them. Scientists pretty much equate photons with electrons because remember how we talked about electrons having like 1/2000th of the mass of a proton or neutron? They're so light, they virtually have no mass, but it can't be matter if it doesn't have mass. So it has just a really minute amount of mass. Same thing with a photon. It says it carries no mass, but it's so minute that it really doesn't seem to weigh anything. But the effect is you see this light. Okay, so a photon, if it's a particle, then it's matter. And if it's matter, it has a mass, even though this says it doesn't. It really does. It's just a negligible mass. Okay, so then we also have these photons. The energy of a photon is going to be giving the atomic emission spectrum. And I also wanted to let you know that Einstein, brilliant man, he actually said that electromagnetic radiation, it has both wave and particle-like nature. The person who is credited to having discovered the particle-wave duality nature of light. So that's just basically saying electrons can behave as either way. And just to let you know, we're going to start studying the Bohr model of an atom, and the Bohr model is going to be based on these different energy levels. Okay, it's very similar to the planets orbiting the sun. We'll get into that later. And then we kind of already talked about this. I don't really want to get into this very much, but the ground state is your lowest energy level. That's the one that is stable. Okay, no energy is radiated here. Then you get to the excited state, which is anything above the ground state, and it's unstable. That's the main thing you need to take from this. And then the last part of this lesson, and then I'm going to close. It's really interesting that we are studying this about electrons. They are so fast, they virtually have no mass, And the Heisenberg uncertainty principle states that we can't know both the speed of an electron and its position at the same time.